Hello Lisbon, this is a message from Google in California. I'm Hartmut Neven, I'm the founder and manager of the Google Quantum Artificial Intelligence Lab. I wanted to thank Volkswagen's CIO, Martin Hoffmann, for having had the interest and foresight to start off our collaboration. We are very much looking forward to it. So this is a very exciting time for quantum computing. In our hardware labs, we have reached the point where we have a sufficient number of qubits and, equally important, an ability to control those qubits to a very high degree of fidelity that we soon expect to reach a milestone that is known as quantum supremacy. Quantum supremacy is a term that describes a situation where you have a quantum processor and it executes a well-defined computational task, a benchmark task, in a short time, let's say in a second, where even the fastest classical supercomputer would take an unreasonably long time, let's say a year, to solve the same benchmark task. So I want to give you some examples where we believe that near-term quantum processors can have an impact for applications in the real world. One area is quantum simulation. We like to refer to this as Richard Feynman's original killer app, because Richard Feynman was the first one to realize that classical computers are ill-suited to model systems where quantum phenomena play an essential role. So in Richard Feynman's words, nature is not classical, goddammit, and if you want to simulate it, you better make your simulator quantum mechanical. So you may say, oh, this sounds rather self-serving, that the quantum computing guys are saying one good application is this simulation of quantum systems. But it is actually very important, because there are many cases where you need to manipulate nature or matter to a fine enough degree that quantum effects do matter a lot. In the automotive space, there's a huge disruption going on moving to electromobility. But as we all know, batteries are still heavy and they still take a lot of time to charge. Now, if you look a little bit at a battery and the electrochemistry problems involved, you find there's a whole bunch of construction sites, so to speak, within a battery that require attention. Currently, there is no simulation ability. That means if an engineer has an exciting idea how to use a different cathode material or move to a solid-state electrolyte, then the only way to see whether this idea worked, he needs to build the system, go in the lab and measure it, which is, by its very nature, slow. So having access to near-term quantum processors may revolutionize this, that now we may have the ability to check a large set of possible cathode materials or electrolytes much quicker and focus expensive lab time only on the most promising candidates. So another application area for near-term quantum processors is quantum-enhanced optimization. Optimization problems often can be so hard because there is often such a huge number of different possibilities that classical computers are just stumped, that they will take way too long time to find a good, let alone the best solution. But using quantum resources, one can actually prove that you can accelerate finding good solutions to optimization problems. So if we can accelerate optimization, we can accelerate machine learning, which in turn is the main discipline of artificial intelligence. We are very grateful that Volkswagen shows this keen interest and the foresight to try to kick the tires of quantum computing and see whether early quantum processors that have passed the quantum supremacy frontier but don't have enough extra qubits yet to do error correction are indeed capable already to do impactful work in the automotive space. So thank you, Martin, for initiating our collaboration, which should be very interesting, and I'm looking very much forward to it. And thank you, Lisbon, for your attention, and enjoy the rest of the conference.